Hello, I'm Niccolò, and this is joint work with Tarmo, Uustalu from the University of Reykjavik, and Zeilberger from the École Polytechnique. And the starting point for our work was the definition of the notion of closed category, which was introduced by Eilenberg Kelly in 1966. So these are categories which come with a unit object, typically denoted by I here, and an internal home, A lolly B here. So we use this notation from linear logic to indicate the internal home or the internal function space. I use this lolly notation. And this is a notion that appears in a lot of examples. So, for example, in categories of structure sets, such as the category of monoids and the category of posets, for example, for monoids, the unit will be just a singleton set with a trivial monoid structure, and then the internal home from A to B will just be the monoid of the monoid homomorphisms between A and B. Another class of examples is given by the categories that underlie inductive systems. The main example here perhaps is the simply type lambda calculus. So now I, the unit object, will be the unit type, and the internal home is just the type of functions from A to B. And in many cases, the internal home actually comes from an adjunction with the tensor product of another category. But in the original definition of Eilenberg and Kelly, this is not required. There is no requirement for the existence of a monodal structure. But if such a structure is present, so if both a tensor and a lolly are present, then when they are and they are related in a nice way, in the right way, then actually the closed structure comes. One can prove that the closed structure comes from the monodal structure. It can be specified in terms of the monodal structure. So this is the theorem that can be found in the original Eilenberg and Kelly paper, which states that if you have a category with a unit I and two functors, so a tensor and a lolly, now related by this adjunction, that to be natural in B, then the pair I tensor is a monodal structure on C, if and only if I lolly is a closed structure on C, and moreover, this adjunction here holds internally. So, as I said before, there is the monodal structure in the presence of such an adjunction. The monodal structure completely characterizes the closed structure. But if you want to characterize the monoidal structure from the closed structure, then there is this additional requirement of the internal adjunction. What does it mean? It means that the following natural transformation here is required to be invertible. And this just states that it's just the fact that this is an isomorphism is the same, is just an internal variant of saying this adjunction. The fact that this is just an internal variant, of this adjunction here. And so if one checks the details of the proof, we'll find out that this requirement is used for defining an inverse for the associator alpha. And in fact, in the definition of closed category, there's nothing that is matching the invertibility of alpha. So that's why this is needed, the internal adjunction requirement. So, but Ross-Street started looking at this mismatch. Let's call it a mismatch. The fact that there is something in the definition of closed of monodal category that doesn't match. That is not matched by anything in the definition of closed category. So Ross-Street started looking into this mismatch, and notice that it is possible to fix it if one consider categories with less structure. So in the definition of a monoidal closed categories, there's too much structure. If you remove part of it, then you'll get a good match. And the weaker variants of monoidal and closed categories that he considers are these two. So the notion of left-skew monoidal categories, which was introduced by this Hungarian algebraist Szlakany in 2012, and he introduced also his own variant, like left-skew variant of closed categories in his paper of 2013 to match the one that matches correctly the definition of Szlakany. And he formulates this theorem that says that now if you have a category that is equipped with a tensor and the lolly, and they're related by usually the same adjunction, then the pair I tensor is a left-skew monoidal structure on C, if and only if I lolly is a left-skew closed structure on C. And there is no internal adjunction requirement. So this is so there is, in this sense, there is a perfect match between the two definitions. And before starting discussing our contribution to this, let's also have a look at the definitions of left-skew monoidal categories and left-skew closed categories. So this is the definition of a left-skew monoidal category. So this is just a category which comes with the unit and the tensor, and now three natural transformations, lambda, rho, and alpha, which have this type, these three types here. And the notable difference with the definition of monoidal category is that these are not required to be invertible, but only natural transformations in this direction that is written down here in the slide. And this has to satisfy all the 5 Maclaurin equations. So there is no way, like in the definition of monoidal category, to dispose of 3 equations and derive them from only 2 of them. So the so-called pentagon and triangle equation of monoidal categories. In here, you need all 5 equations of Maclaurin. And then there is also a notion of a left-skew closed category. This is from Street. And so again, it's a category C. We now have a unit, a lolly, and we also have this 3 natural transformation, J, I, and L, which have this type. And they have to satisfy 5 equations. So now these are, this J, I, and L are also required to, there are structural laws that appear also in the definition of closed category by Eilenberg and Kelly in the original definition, but in the original definition there are some additional requirements. So first of all, I is required to be an isomorphism. So there is an isomorphism between any object and A and I lolly A. And then there is another requirement. So clearly here it doesn't make sense to ask for J and L to be invertible. So J in principle intuitively is just a function on the intuitive level that picks out the identity, the internal identity from A to A, and L it's something that just performs post-composition. So take something of a function from B to C and the function from A to B and then compose them. So there is no reason why these two should be, J and L should be invertible, and in fact they're not required to be. But in the original definition, one also takes something that can be derived from J to be invertible, which is this J hat, which now takes a morphism from A to B in C and returns a morphism from I into A lolly B. So somehow it's a way of turning an external morphism into an internal morphism. And it's defined as using J in this way. So by applying first J and then post-composing with the identity lolly F. And this is required to be invertible as well in the original definition, so of closed category. But while in here, neither I nor J hat are required to be invertible. So right now with the definition in place, we can continue and talk about our contributions. The first contribution the following. So it's talking about trying to basically prove refined variants of the street theorem, including normality conditions. So what is a normality condition? So, for example, in the Left-skew monoidal case, we call a normality condition the invertibility of a structural law. So either rho, lambda, or alpha, or more of those, or multiple of those. And notice that one obtained the definition of a usual definition of monoidal category by just requiring all the normality condition to hold, so that all three structural laws are invertible. And then, as I said before, we also managed, so we can prove a version of Street's theorem of the Eilenberg Kelly theorem, including normality condition, because we managed to find what does it mean? What are the analog of the normality condition of the skew modal categories, less skew modal categories in the Left-skew closed setting. So, and more precisely, we have this theorem. So now in the presence of an adjunction, as before, now not only there exists an isomorphism between the Left-skew monoidal and the Left-skew closed structures, but now the skew monoidal and the skew closed normality condition also correspond. There is a one-to-one correspondence between those. So let's be more precise. Let's see the precise correspondence. So this is in the Left-skew modal setting, okay, for the Left-skew modal structure, and this is the conditions for the normality conditions for the left skew closed structure. So the invertibility of rho corresponds to the invertibility of I, and the invertibility of lambda corresponds to the invertibility of j hat. So these are the two conditions of that are usually also required in the definition of closed category. But then we managed to also find a normality condition associated to the invertibility of alpha in the Left-skew closed setting, which is the invertibility of this L hat, where L hat now is this definable, this derivable morphism, right? Going from this coend here into this other concept, and again, of course, the invertibility of alpha is also equivalent to the invertibility of P, so to the fact that there is an internal adjunction. So, but the invertibility of L hat, this was the missing piece somehow in what created the mismatch. So if we ask, for example, if you add to the definition of closed category also the requirement that L hat must be invertible, then one gets a perfect match. So with the definition of monoidal category. So this new definition of closed category will match precisely with the definition of monoidal category in the Eilenberg Kelly theorem. So, and notice, so how do this L hat and J hat things arise? So these are actually interdefinable with J and L respectively. So we saw before that J hat can be defined in terms of J, but it's also true the opposite. So if we take J hat as primitive, one can also derive J. And this is the case also for L and L hat that are also interdefinable. So one in principle can define, can have a definition, an equivalent definition of Left-skew closed category, not in terms of I, J, and L, but in terms of I, J hat, and L hat. And then talk about normality condition, asking for any of these three structural law to be invertible. So so maybe I can give some intuition on what does it mean to be, for example, for the inverse of L hat. What does the inverse of L hat do? So it takes a morphism from A into B lolly C lolly D, and it returns an element of this coend. So it's an object X and two morphisms here. So the idea here is that X should be a form of weak tensor of B and C, right? Because then you have a morphism from A into X lolly D. So if you think of some B tensor C here, then this is what one will expect. And again, and here is a way of embedding B and C into the B tensor C. So it's kind of some kind of the existence of a weak tensor. The invertibility of L hat corresponds to the existence of the tensor of B and C. But interestingly, if you look at the first morphism here, this offset here, we are actually allowed to eliminate this tensor only into D, not in any other object. So this is, in this sense, this is a weak tensor. And so yeah, so as I said before, we can substitute the internal adjunction requirement in the original Eilenberg Kelly theorem with the invertibility of the hat, and then we will have a perfect match. So if we ask for this invertibility of the hat also in the original definition of closed category. Interestingly, this condition was already identified in the past by Day and LaPlaza, and it appears in a couple of places. But then we didn't manage to actually find it after the 70s in the literature, so it was kind of lost. And so the second contribution of our work is the fact that, well, nothing forbids us in principle to just swap the orientation of all the structural laws in the left-skew monoidal category, and one will obtain something called the right-skew monoidal category. So when now the structural laws are all in the other direction, and yeah, there are some 5 equations analogous to the one before. But then it's more interesting what happens if you do the same thing with the left-skew closed category. So we just swap all the structural laws. So we start with the definition taking I, J hat, and L hat, and just swap the orientation of those, and one will end up with the notion of a new notion of right-skew closed category, which has this as primitive structural laws, satisfying now also some 5 equations. And well, again, we also proved a theorem that it's like a right-skew variant of street theorem, that now you can connect adjoint right-skew monoidal and right-skew closed structures on a category. And also there are some similar relationships between the normality conditions. But more interestingly, so we can prove a new theorem that now connects left-skew closed and right-skew closed structures on a category. So it goes as follows. So if you have a category with a unit and 2 lollies, so we indicate with lolly L and lolly R here. So and together with the following condition that we call the external lambic condition, which says that there is a bijection sigma that is natural in A, B, and C of this form. So this takes a morphism from A into B lolly R C into a morphism from B into A lolly L C. We call this the external lambic condition. And why is lambic involved in this is because if one looks at because this is very much reminiscent of something that is actually of a characteristic feature of lambic syntactic calculus. So it's something that it actually holds in there. And if you look at what it says, it's basically it says that A and B can be swapped here, but if you do that, you also have to swap the lolly. And this holds in the lambic calculus, where now instead of the lollies you have the 2 residuals in that case. And then if you have this condition in place, then I lolly L is left-skew closed, is a left-skew closed structure on C, if not if I lolly R is right-skew closed structure on C. And again, there are some correspondence between the normality conditions. Now, for the left lolly, if the I of the left lolly is invertible, then this is the same. This is equivalent to asking for JR of the right lolly to be invertible. And if J hat is invertible, then this is equivalent to IR being invertible. And then you have also a condition for the L. So L hat is invertible if LR now is invertible. And moreover, and this is also equivalent to the existence I mean, something that is kind of analogous to the internal adjunction condition that we saw in the original Eilenberg Kelly theorem, which is the fact that the following morphism that is derivable using L hat or using LR is actually an invertible. And look, if you look at what it is, this is just an internal version of our lambda condition. Right? It's just this is an internal version of this lambda condition. Okay, so you can swap A and B here, but you have to swap also the only L and the only R. Okay, so now let's move to the third contribution, so which is examples. So in this paper we give a very large number of examples because we need to motivate the different normality conditions, as also the new notion of right-skew closed category. So in this talk, we will focus on 3 classes of examples. So the first it goes as follows. So you're starting with, for example, left-skew closed category. How can you further skew it to the left using a comonad? Or if you start with a right-skew closed structure, how you can skew it further to the right using a monad. Then we'll see how, starting from a skew closed category and monad on it, how to lift the skew closed structure onto the Kleisli category of the monad. And the third example is the non-commutative linear type lambda calculus unit type. Okay, so here we start with a left skew closed category, C and I lolly, and a comonad D on it. So we want to generate, come up with a new left skew closed structure on C using D. And we can do this if we ask for D to be lax closed as well, which means that it comes with a map E from I to DI, and the natural transformation C from D of B lolly C into DB lolly DC. And it has to be coherent suitably with the data of the left skew closed category and the co-unit and co-multiplication of the comonad. And if we have this lax closed, the comonad is lax closed, then you can define another left skew closed structure on C, where the unit is the same, and now the lolly is given it's given as follows. So it just B lolly C for this new lolly is just a DB lolly C. This is the old lolly to apply the comonad to B. And then we can derive, for example, this is how you derive the new structure of I in this case. So you first apply E here, because you go from I to the I, and then you apply you post-compose it with I applied to A. But this I is the I of the original left skew closed structure. And then one can start asking how the normality condition lift to this new structure. So yeah, so for example, if I is invertible, when does the new I is invertible, for the new structure is invertible? Well, this is true if, for example, if A sufficient condition is E to be invertible as well. And one can play a similar game, starting from a right skew closed category and starting with a monad instead of a comonad, and asking for it to be Oplax closed, and then one will get a new right skew closed structure on C defined in this way, where the lolly is defined in this way. So again, now instead of applying D to B, just apply T to B. Okay, the second class of examples. So we start with the left skew closed category and the monad. And if the monad, and so now we will ask, when does this left skew closed structure lift to the classical category of T? And this is the case if T is left strong. Or alternatively, people call this internal functoriality, which means that there is a natural transformation of this form. So from B to C, B lolly C into TB lolly TC. It is also suitably coherent with the data that we have from the category and from the monad. And now we can define a left skew closed structure on the Kleisli of T, the Kleisli category of T, where the unit again is the same, and now the new lolly is given by just applying T on C now. So B lolly C with new lolly is B lolly TC. Well, this is the old lolly. This is how you define J and I for the new closed structure, left skew closed structure. So I is very simple. You just use I on TA. So the new I on A would be the old I on TA. And for the new j on A, you first apply j, so you go from I to A log A, and then you apply eta here on this A, and you go into A log A. But now this has to be amorphous in the Kleisli category of T, of T. So then you have to, so this is a pure map, you just use J, which is the functor embedding C into the Kleisli category of T on this morphism, and then you get something that is well typed. And again, one can play the same game by starting with the right-skew closed category and obtain the right-skew closed structure on the Kleisli of T if now T is lax closed. Okay, so the last example is the actually it's a restricted variant of the non-commutative linear type lambda calculus with unit. We'll see in a second why is it restricted. So this is how this goes. So the objects of this is to construct a category. So the objects are types. This is the grammar for types. You have atomic types, unit and volume, which is this function spaces here. Contexts are or antecedents are listed types. This is the grammar for well-formed terms. So you have variable, and then you have unit, introduction, and elimination, and abstraction and application. So you see that this is a non-commutative linear variant of simply type lambda calculus. You can see, for example, in that rule for application, because first of all, the resources that we have in context split so part of them go to the as resources for the function argument for this t here, and the second part goes for the argument of the application, and they go in order, right? So gamma goes to the left and delta goes to the right. So this is why it's non-commutative. But I said before, this is actually a more restricted version of the non-commutative linear type lambda calculus with unit, because there is an additional restriction on the unit elimination, and it is that now again this is a similar restriction that we have here. So the gamma so you have we have T of type I and U of type A, but the resources of T, so the context of T, must come from the leftmost position, from the left side of the context here. So gamma cannot appear in any position of the context here, which is usually what you have in the usual non-commutative linear type lambda calculus. But in here, this is more restrictive. And definition of equality of terms is beta equality, and now so the morphism of these categories are now well-typed equivalence classes of well-formed terms modulo beta equality. So for example, this is a Left-skew closed category, and this is how you derive L, for example. Right, so you're given in context x of type B log C, and you want to derive this. And this is just lambda y, which is type A log B, lambda z and z at type A, and then just apply x to the application of y to z. And this is all typed. One can check in the derivation tree here. And this is a nice example because also is a concrete presentation of the free Left-skew closed category that is generated by the set of atomic types. And interestingly, in this example, there is a normality condition that already holds, which is the invertibility of j hat. And what does it mean in this setting? It means that there is a bijection between closed terms of type A log B, so closed functions, and open terms of type B with one free variable in A. So this is what this invertibility of j hat tells us in this setting. And one also may wonder, what about the invertibility of I, for example? Well, this is obtained by relaxing the elimination rule for the unit with this more permissive rule, where now, the gamma in the context of T can appear anywhere in the context in the context of the conclusion here. You see, before it was restricted to be on coming from being the left part of the context, but now gamma can be anywhere in the context. And if you add this rule, which gives the invertibility of I and the associated left-skew closed structure, one gets the full non-commutative linear type lambda calculus with units, or what one usually calls non-commutative linear type lambda calculus with unit. Okay, so this concludes my talk. So we continued working on clean variants of Eilenberg Kelly theorems. That was something that Ross Street started working on, and we proved that there is a relation between left-skew monoidal structure and left-skew closed structure, also with partiality conditions, with partial normality conditions. Sorry, and also we, for example, we demonstrated that that is also interesting to consider right skew variants of this of monoidal and closed categories, in particular closed categories. So once we do with analysis, this notion comes out naturally, and we justify these notions with a big number of examples. And what we would like to do next. So first, we would like to come up with a number of examples that are relevant to the semantics of programming languages. I mean, there must be, so we showed that there are several examples involving monad and co-monads. So we believe that this is a good path for future work. And we also would like to continue what we've done already. And we presented it 2 years ago at MSFP, and which is where we developed the proof theory of left-skew monoidal categories. And we would like to also do similar analysis, proof-theoretic analysis of also left-skew or partially normal monoidal, and what are also closed, monoidal closed, biclosed, and symmetric monoidal categories. Okay, so this concludes my talk. Thank you for listening.